Can everybody see the screen?
Yes, that's good.
Okay, great. Okay, thanks again for having me at your workshop. As Sanjay said, we are trying to get that organized for years, but it never really happened. So I'm very glad that this time we were able to organize things. What I'm going to talk about today is how we can do asynchronous programming in modern C++. And what I'm especially excited about is to show you some things, how the now accepted C++ 20 standard and the language features that have been introduced in that standard can help us to simplify writing asynchronous code. Because so far it was always a problem to write asynchronous code because you somehow had to take your brain out, turn it around inside out, and plug it back in order to really understand and write asynchronous code. And that will be much, much simpler with the upcoming language features that will be available hopefully soon in the compiler you work with. The picture here on that screen is a still image from a simulation of one of our HBX applications. It's a double white dwarf system. And you might be interested why I'm showing that. Well, our astrophysicists are very excited about being able to simulate these white dwarf systems because they are assumed to be the progenitors for the supernovae of type 1a, which is very important for the astrophysicists because it allows them to measure distances in the universe, which wouldn't be, oh, it's just one method of measuring the distances. And that's a very important thing to do. Okay, let's get started. If you look at parallel applications and at the tools available to us when writing parallel applications, then especially in the C++ world, we are faced with a multitude of tools that usually don't fit very well together, that are badly integrated with the C++ language, and in general have a couple of flaws I will elaborate about in the next slides. Also, if we look at even at applications that we believe are nicely parallelized, we usually see this kind of behavior in the utilization of your machine. What that image shows is the utilization of a couple of cores in a typical application, where the green bars show that the core is busy and the white gaps in between the green bars just indicate that the cores have nothing to do. And this is a fairly common thing we have experienced and have seen in many applications where the programmer said, oh, I really parallelized everything. I'm using all the 48 cores I have on my node. But if you look closer, you will see that there's a lot of gaps in the resource utilization. And I will talk about that a bit more, how that can happen. So in real world applications, we usually have the problem that we have insufficient parallelism. And the big problem here is that this insufficient parallelism is, in part at least, imposed by the programming model we are using. And I specifically talk about OpenMP here and MPI. OpenMP as the go-to parallelization framework for on-node parallelism, MPI as the go-to library for distributed parallelism, both of which are very badly integrated with C++. And I'm very happy that the C++ community over the last years has caught up and has tried and succeeded in part in creating tools that very nicely integrate with the C++ language. And we will talk about them later. What's the problem with OpenMP? And just let me say a word before I actually continue. On this slide, I usually have at least one person in the room that gets really, really upset. Because how can I dare to criticize OpenMP or MPI? My point here is that OpenMP and MPI are very, very flexible and very widely used. that, on the other hand, a naive use of those tools usually leads to problems that limit the parallelization and the resource utilization. And it takes a lot of effort and a lot of expertise from the programmer to overcome these limitations, so that both OpenMP and MPI don't give you full resource utilization out of the box without additional significant effort on the programmer side. One example here is the enforced barrier at the end of the parallel for loop in OpenMP. And yes, I know about the no wait clause, but it's kind of useless because, again, you have to do your own programming in order to find out when the loop actually is done. Or in MPI, in many MPI applications, you have that global communication barrier after each time step that puts all nodes into lockstep and makes the application wait for the slowest node before it can continue to the next time step. We also see that we are over-synchronizing by waiting for more things than are actually required by the algorithm. Well, as I said, the lockstepping between nodes is a clear over-synchronization because most of the time, some of the nodes could actually go ahead to the next time step without any problems, but the global barrier prevents us from doing so. Also, there's insufficient coordination between the on-node and off-node parallelism. Have you ever tried to call an MPI API function from an OpenMP thread? If yes, then you know what I'm talking about. So there's insufficient co-design of the tools going on, and that not even talking about adding things like CUDA or HIP or other toolkits, which all give us different distinct programming models for different types of parallelism, which is a major pain for the programmer. Okay, what challenges do we face? We need to design a programming model and programming environment that exposes an API to us that intrinsically enables overlap on computation and communication without additional effort on the programmer side, which enables fine-grained parallelism so that we can utilize our resources much better, which requires minimal synchronization between dependent things so that only the things that are needed to be computed are taken into account in the decision what to do next. We need tools that make data dependencies explicit because only that allows for the system to decide properly what are the next tasks to run. And we need manageable paradigms for handling parallelism, because if you start talking about fine-grained parallelism, you start talking about millions of threads, and no sane person can handle millions of threads and can reason about millions of threads at the same time. And also the additional challenge I am seeing is that all of that has to integrate well with the existing C++ language and the standardization efforts. Asynchrony is definitely one of the factors that can help improving the resource utilization of our machines, but it's not sufficient alone. We need also facilities for efficient parallelization, for efficient creation of threads, for efficient composition of asynchronous tasks, sequential and parallel composition, we will see that in a bit, and efficient synchronization between threads, and certainly facilities that give us the means of asynchronous data transfer between threads and between nodes. All of that really integrated into the programming model so that, as I said, the programmer doesn't have to invest additional effort in order to get these nice features. That should be kind of be automatic if you follow the programming model that the system gives you. We have taken all that, or have tried to take into account all these problems and all these ideas while developing HPX. So it has been developed kind of from first principles. And today is one of the available asynchronous many-task runtime systems. As Sanjay said, next to Charm. Well, I'm not going to list all of them here. There are many available. And the sad story is that essentially each national lab develops their own runtime system, and some of the labs develop more than one runtime system at the same time, which is really, really funny and interesting to watch. Okay, so what is special about HPX? We call it the C++ standards library for concurrency and parallelism. And that is for a reason, because what we've done, we have tried to expose a coherent and uniform API in a very standards-oriented way, meaning that if you take a standards-conforming C++ program that uses the C++ standard library, and you change some of the namespaces in your program from std : to hpx : you get a fully functioning program again, with a nice side effect that it usually runs faster. One of those, well, just one example for that, we work with Oak Ridge National Labs on a quantum Monte Carlo simulation, which is called DCA++. And there, just the change of the namespaces has given us a speed up of about 20%, which is quite amazing. And that API we expose can be used for local parallelism, for distributed parallelism, and also in heterogeneous applications. That DCA++ application, for instance, is very heavily using GPUs. It's running on Summit, and it's utilizing the Summit GPUs to a large extent. So HPX enables you to write fully asynchronous code using hundreds of millions of threads. And the important piece is that it gives you a unified syntax and semantics in terms of local and remote operations. If you follow that programming model we have developed, you essentially get an emergent autoparallelization property out of that. And I will highlight that in this talk a bit. A quick structure of HPX, not too many words about that. 4 major blocks: is threading, subsystem, synchronization. We have a global address space, which allows us to move things around, and a networking layer. All of that exposed to the application on top through a concurrency and parallelism APIs that are conforming to the C++ standard, and tied together with a performance counter framework that can be used to drive engines, policies, to control and to introduce runtime adaptivity into the system. Just as a example, how does an API look like? If you know the C++11 or newer standards, then you know about standard thread, mutex, future, async, and so on and so on. And we have all these facilities available in HPX as well. And you might ask, why did we implement things like std function or std any again? Well, we want to extend the APIs the standard gives us for the distributed use case. So in case of std function, you can bind an HPX function on one node, send it over the wire, and execute it on the other node, which is very interesting, very powerful, very C++-like, helps writing modern C++ code. One important part, and that's where the C++ community recently has caught up with the parallelization necessities of applications, is the introduction of parallel algorithms into C++ 17. We know all the algorithms in C++ since late 90s. But now finally, those have been extended to give you parallelism. And the way they have done that is that all the algorithms now have an additional argument, the first argument, which is called the execution policy. There are several execution policies introduced by the standard. I will highlight only 2 of them here. One is par, the parallel policy that instructs the system, the runtime system, or the library to parallelize a particular loop, or sec, just if you want to force one of those loops to run sequentially anyway. A quick example, standard fill takes begin and end of the range to fill with zeros. And in order to parallelize that loop, all you have to do is you pass an additional argument to the algorithm. The same pattern has been applied to all the other 150 algorithms the standard has. Now, you might say, this is still fork join parallelism in the same way as OpenMP introduces, and in the same way as OpenMP introduces a barrier after the execution. This mode of operation still introduces that barrier. And that's one point where we have tried to extend the things in the standard in HPX, and I will give you an example for that in a second. So let's look at two more examples. This is the one I just showed you. Just fill the vector with zeros. That doesn't give you much control over where things run and how things are being scheduled. It just tells the system, hey, you parallelize that in any way you like. I don't care as long as it runs faster than before. In HPX and aligned with ongoing standardization efforts, we have added additional customization possibilities to that parallelization scheme. The user can write what we call executors, which are essentially very simple objects that decides how, where, when, and in what way things are being scheduled. And you can attach your executor to the par execution policy and customize the algorithmic execution that way. Often you want to additionally influence affinities, chunking, scheduling, and so on. And you can do that by writing some special customization object, some parameters object, which can be attached to the execution policy as well. In what we have done in HPX, we have extended the execution policies to be asynchronous, and that really mitigates the fork join parallelism disadvantages. Because what these asynchronous execution policies, par task and sec task as an example, do, they turn the formally synchronous functions and algorithm invocations into a function that returns a future. So you just kick off the operation and get a future back, which represents the end of the execution of that algorithm. So the parallel construct is executed asynchronously, and that helps with improving the utilization of your machine, because while the parallel loop is tapering off or synchronizing or waiting for all the iterations to catch up, some of the cores are being freed up naturally, which before has led to diminished resource utilization. But since this is executed asynchronously, other work can be started in parallel or concurrently and can take over the cores that are freed up by the loop execution. And that certainly allows us to integrate that into a larger asynchronous control flow, as I will show in a second. So let's talk about futures. And I have shown that many times, so I will be brief. Let's assume we want to calculate the universal answer. So the answer to life, universe, and everything else, which we know from the literature, is 42. But the drawback is that the calculation of that 42 actually takes 7.5 million years. And nobody wants to wait for 7.5 million years without doing anything else. So we construct a computer we call Deep Thought. And the thing that Deep Thought computer does, it uses async to create a new thread to launch the universal answer function that will start running on a separate thread. Then we can go on with our lives for said 7.5 million years. And once we are sick and tired of waiting, we call .get on the future object that was returned from async. And .get can do two things. Either the answer has been computed, then get will return immediately, or the answer has not been delivered to the future yet because it's still running, it's still computing. And in that case, get will suspend and will return only after the value has been delivered. This is very, very nice because it allows us to stop thinking about threads. All we do, we kick off a new operation, and when we need the value, we call get on the future. and it will give us a value whenever it's there. And the current thread is being suspended so that the core can do other things while the current thread is being suspended. So schematically on the left side, this is kind of depicted. You have a future object that is suspended at some point. The second locality is doing the execution of the tasks the future represents. And whenever the value comes back, we resume the original consumer thread and we can continue, which gives us a very nice, transparent way to synchronize with the producer and hides the notion of dealing with threads. That is actually very important. Equally important is that in this context, the future represents a data dependency, because the code that depends on the result will run only after the future has been made ready. If you look at Intel's parallelization efforts, or the efforts to create parallelizing compilers, you will see that Intel is promising us that for 50 years now, and they don't really get everything under control that easily. The reason is that the compiler doesn't know anything about the control flow in the application, and the compiler tries to reconstruct the pieces in the original code that can be run independently. And that is an almost impossible task because, well, the compiler sees only the written code and doesn't understand what the programmer had in mind. So if we have a way to convey the data dependencies to the system, then the system can automatically parallelize things because, well, in order to do something, there are two things have to be finished before. And once these two things are available, then the system can schedule the dependent tasks. So futures are perfect for that. Let's look at an example. So I chose Quicksort because it's computer science 101. Everybody can understand it, everybody knows it, and it fits on a slide. So let's parallelize Quicksort. We assume that we want to sort a sequence of values that are contiguous in memory between first and last. So we are dealing with random iterators here, random access iterators. We certainly want to sort things only if we have more than one element in our sequence. So how the easiest way to implement Quicksort is to select a pivot point, which in this case we select the middle element in our sequence, assign it to P, and then the lambda we pass to partition gives us is a predicate which tells us whether the current value is actually smaller than a pivot point or larger or equal to the pivot point. We use the STL algorithm partition here. Partition is a very nice and powerful algorithm because it reorders the elements in a sequence in a way that everything that's smaller than a given, or everything for every element for which the predicate returns true will become first, and all elements for which the predicate returns false will come after. So the predicate here, in that case, that lambda is being called for all the elements between first and last, and partition reorders the elements. So what we get after partition returns is that all elements that are between first and pivot are smaller than all elements that are between pivot and last. So partition returns the iterator pointing to the actual partition point in the sequence. And all we have to do afterwards is we call Quicksort recursively for the left and the right subpart. Done. So we have a very nice sequential implementation of Quicksort with a couple of lines. Please note that you certainly can use more sophisticated algorithms to decide what pivot point to use. In this case, I just chose the simplest one, so it fits on a slide. Now let's parallelize that. We do the same thing. We have we additionally introduce a threshold to maintain grain size because it doesn't make sense to parallelize things if you want to sort only a couple of elements. So we do the parallelization only if we have more elements than a certain threshold. In the case of if we have too few elements, we just call sort with the sec execution policy, so it will sort sequentially. And otherwise, we call partition with a par execution policy, which will parallelize the partitioning process as explained above. Well, and then we do the quicksort to the left and to the right. You might say, oh, great, done. I have parallelized my quicksort. But the point is that this quicksort is exactly exposing the behavior I showed in my image in the first place and on the first slide, that you have kind of bursty activities whenever partition is executed, but you have these utilization gaps in between. And now let's have a look how we can overcome that. What if we create a quicksort algorithm that actually returns a future? So a quicksort that kicks off the computation and returns essentially immediately. The scheme is the same. If we have more elements or less elements than the threshold, we sort it sequentially. We just do it sequentially. In the end, now remember, we have to return a future. So in this case, we just return a future that is ready to begin with. There's a facility function which is called makeReadyFuture. So that's not very interesting. Now let's have a look at the parallelization part. And here things get a bit more interesting because I'm using the par task execution policy now, which means that the partition algorithm is launched asynchronously, and it now returns a future that represents the result. Now, the code I will show now is a bit difficult, but please bear with me. I will simplify that significantly on the next slide. Since partition now returns a future, we can't immediately call quicksort on the left and the right subsequences because the partition has to finish running before we can do the recursion. So what we do, we use the pivot.then function, which is a facility that we have added to the future object. That allows us to attach a continuation to the future. That means whenever the future becomes ready, this lambda in this case is called automatically without us having to do anything. And when the lambda is called, we know that the partition operation is finished. So what we do, we call quicksort on the left and on the right subsequences. But remember, quicksort now returns a future. So we have to somehow combine these futures into one future, which is can be done with the when_all facility. And when_all gives you a single future that will become ready when all of the futures it was invoked with have become ready. So it is a means of parallel composition of futures and tie them together into an execution flow. Now let's have a look at what we have actually done. We have turned our initial quicksort function from a function that returns only once it's done into a function that returns essentially immediately and gives you a future representing a data dependency tree, because the return future depends on many futures that one from each recursion essentially. So we have turned the sequential execution into a futurized execution that first creates a tree and then unravels the execution tree in without additional or without unneeded synchronization, which is the important piece here. Now let's simplify that code a bit. And I said in the beginning, I'm very excited about the C++20 features. While the code on the previous slide was very complex and very difficult to write, what we can do now with C++20 that introduces a co-await keyword. And the nice thing about co-await is that you can make it do exactly what I was explaining before. So all we have to do now, we have to co-await for the partition to finish, which gives us the pivot point. And then we do the recursive quicksort to the left and to the right and co-await on the overall future return from when_all. Done. And if you compare that code to the initial sequential code, you will see that there are almost no changes, but we have a fully parallelized code that runs as fast as you can and exposes very nice utilization characteristics. Okay, so I mentioned asynchronous communication in the beginning. Just one slide on how we manage asynchronous communication. We created facilities which we call channels. We have stolen them from Go, from the language. And what they do, You can create a channel on one thread or on one locality. You send it over the wire, and on the other end, you refer to it from another thread. And the channel essentially has two API functions, get and set. And both of them return futures. So the set side returns a future which becomes ready when the channel has accepted your value, and the get end of the channel returns a future which will become ready whenever data has been delivered through the channel. And that allows you to integrate these asynchronous communications between localities or even between threads very nicely with your asynchronous execution flow. Another example. I have to explain a bit more for this example because we are talking about a project that is we've been working on for the last years, which we called Phylanx, a system that allows you to asynchronously execute distributed array processing. So essentially a distributed machine learning framework, allowing to scale out your machine learning problems across clusters. And that's kind of first. There are some attempts in the community to actually create distributed machine learning toolkits, but none are really successful at that so far, from what we can tell. Very quickly, Phylanx is tries to solve the problem in machine learning that the main scientists know their topics, but they have trouble getting their things run on high-performance computing resources because we need to make the algorithms distributed, which requires data tiling. The domain scientists usually work in Python, but we want to execute things as fast as we can on a C++ execution engine on a cluster. So our goal was to abstract away the complexities of programming on high-performance computing resources from the domain scientists. And we have done that by integrating Python with a C++ execution engine based on HPX. It's built on top of many parts: HPX, Blaze, linear algebra library, Agave to submit things to the resources, Jupyter notebooks for the front ends. So what we have done there, we have combined the performance of HPC systems with the ease of programming in a higher level language, in Python in this case. So the Python front end abstracts away the complexities of lower level implementations. We integrated with Jupyter notebooks. So we are able to run NumPy code directly in Phylanx. We create distributed task graphs from the Python code and use HPX as the execution engine to execute the task graphs that are created. Let me show some schematic, or let me give you some schematic explanation what we do there. Phylanx builds a system that consists out of three parts: the front end, where you have a normal matrix expression, A and B in this case, a middleware part that uses an internal representation like an abstract syntax tree or MLIR to walk the tree, to optimize it, to do additional things to transform these internal representations. And from that, we create a distributed execution tree that is evaluated using HPX. In practice, that looks like this, for instance. So in Python, we would decorate our function we want to distribute using the @Phylanx decorator. That is transformed into some intermediate representation, which is very similar, has drawn from Scheme. So it's a very functional representation. And that is turned into a HPX execution that uses Dataflow and other facilities to run the execution tree at full speed. And I will give you a code example later. As I said, that can be run from a Jupyter notebook. You can run it from your interpreter, or you can, if you're really adventurous, you can directly use the C++ API to program it. The middleware is meant to apply various transformations to the internal representation. We want to do optimizations there. We want to automatically decide on how to tile the data and how to distribute the data. And we would like to create a bridge to MLIR here to feed, to use the execution engine with other tools that produce MLIR, that machine learning intermediate representation that is being standardized currently. The goal of those optimizations is to minimize computation and communication between the nodes. And the trick is that this is specific to the expression to be evaluated. So we look at the expression and try to optimize the execution for this particular expression. And we can also store the results of the optimizations, so we don't have to redo that over and over again. The backend, and that's what I want to focus on here, uses adaptive asynchronous execution using HPX, obviously in C++. So if on a single system, on a single node, we have the A minus B expression and it's being evaluated as an execution tree with 3 nodes, the minus node, the nodes that represent A and B. And when evaluated, when you want to evaluate the minus operation, you first evaluate A, then you evaluate B, and deliver the result to the node above. In a distributed system, you deal with tiled data. There we cut the matrices A and B into pieces and put A prime and B prime on one locality and A double prime and B double prime on another locality, and create an execution tree that acts on the parts of the matrices separately. And you can join it afterwards in some way if you want, some reduction operation or whatever. These trees are distributed across the system. So the left tree runs on one node, the right tree runs on the other node, concurrently, obviously. And you obviously, and that's what we have done as well, we have integrated that with Docker or Singularity so that you can submit that not only to clusters, but also to cloud resources from your Jupyter front end. And here's just an example. This is some support we built into the Jupyter notebook. We call that Traveler, where you take some Python code. You can submit that Python code through Agave and Tapiz to a remote resource. You wait for it to be executed, and you get back a link. When you click on that link, you get visualizations of the performance information that was collected while your code was running on the remote node. And here are just a couple of images that depict the various presentation views provided by that system. Very important to look at, or a very important tool, especially in the task-based runtime system arena, because there are no real debugging and performance analysis tools available that allow you to tie the task nature of your execution into the higher level representation of your Python code, or even higher level C++ code. The last figure here shows you the visualization of one of those execution trees, and the colors depict the amount of work that was executed for that particular node. Okay, so let's look at a distributed execution model we have in Phylanx. As I said before, there we had an operation that didn't require communication between the localities because it was an element-wise operation, namely just subtracting one matrix from another. What if we want to do a dot product between two matrices? Well, in that case, things are a bit more complex because besides duplicating the execution tree, we also have to communicate between the nodes in an asynchronous fashion while running these two trees on the two localities concurrently. So the nodes communicate as needed in order to orchestrate the dot product as needed. And we have created quite a list of those primitives. We call those primitives, these things which are in a circle here, to perform a wide variety of operations. And we can essentially translate NumPy code directly to to that execution engine and run it on a cluster. Now let's have a quick look at how that looks from the code standpoint. What I have here is a struct which represents one of those primitives, one of those nodes. And I want to look at the add, quickly show you how the add node is implemented in a very high, on a very high level without too much detail. As you can see, add is derived from a HPX facility, which we call component. And an HPX component is a C++ object you can talk to remotely, and you can create remotely, and you can schedule things to work on remotely. Excuse me. Now, what these primitives expose is essentially a single function, which we have called eval. Eval is being invoked asynchronously and is supposed to return the result of a computation for a particular node, for the add node in this case. The parameters, we can ignore them. At this point, that's additional function arguments that might be needed for other evaluations and not for the add node. But the add itself has a vector as a member that represents the child nodes of that add operation. And in this case, I just assume that I have two children attached to the add node. So once eval is called, once the add operation is to be evaluated, we launch the left and right evaluation, or the evaluation of the left and the right child asynchronously by creating new threads. Those give us a future. And then we use co-await on the left-hand side and on the right-hand side, and return the overall result to the node that has invoked the add operation. Again, the code looks very much like the synchronous code you would write if you had to do that in a synchronous fashion. Very straightforward. It enables us to convert synchronous execution into a fully parallelized asynchronous execution without too much effort, thanks to C++20. Okay, another example for that, let's assume we have a CUDA graph we have created from somewhere which represents a subtree in our execution graph. And we can do the same thing. We just evaluate all children. I'm using a special facility function map here. Map concurrently evaluates all elements in the children vector and returns a vector of futures where each future represents the evaluation of one of those children. When all is then used to combine that vector of futures, and we co-await on that single future to get the results of the evaluation. And then we pass these results of the evaluation to some facility function that takes the graph and the arguments and evaluates the CUDA graph on the device. This is just to depict a possible example how things can be, how special accelerators can be integrated in the evaluation of the overall execution graph. So as we have seen, there are many ways to add a synchronous execution to our applications. And to recap, I have introduced a technique we call futurization that allows us to automatically almost automatically transform code by delaying the direct execution in order to avoid synchronization. It turns the straight code we had before into futurized code, which no longer calculates the results, but just generates an execution tree that represents the original algorithm. And if the tree is executed, it produces the same result as the original code was producing. So the execution of the tree is performed with maximum speed because we avoid any unnecessary synchronization, and we can overlap all the computation very nicely because there's a lot of parallelism available in the system. And here we get to the point where that execution kind of exposes an emergent property of almost being auto-parallelized because of the scheduling we use in HPX, which is a commonly known work-stealing scheduler. We can redistribute all the parallelism very nicely on the localities. Some recent results. I showed you that execution graph before. One problem, and as you have seen in the code example I gave you, each of those nodes launches a new thread in order to evaluate its children. And obviously, this can very quickly lead to unnecessary overheads, especially if the children have to perform only very little work. What we have looked at is to introduce some runtime adaptivity here by measuring the execution time for each of the nodes and deciding on that execution time whether to actually launch a new thread when the node is to be evaluated again, or whether we can inline the execution of a certain subtree of the overall tree into the parent thread. And that was very successful because what we have seen is that depending on the problem sizes, we get quite significant speed up if we start inlining tasks based on a adaptive threshold that is used to decide whether to synchronously or asynchronously evaluate a certain subgraph of the tree. This is just an exemplar graph. We have seen these significant improvements across the board, actually regardless of what concrete expression or what concrete algorithm we have tried to evaluate using Phylanx. Another two graphs give you the scaling behavior of Phylanx on a single node. The blue one is the Phylanx execution. The green one is a non-distributed alternating least squares algorithm written in Python using NumPy. As you can see, the Python implementation using NumPy doesn't really scale well, whereas the Phylanx implementation scales very well up to 48 cores. The very same code can be run on a distributed system, in this case up to 64 nodes, each of them using 48 cores. And as you can see, the scaling behavior is very nice as well. And the larger the problem size we are working with, the better the scaling behavior across the board. Again, this is just one example here using a alternating least square algorithm, but we see very similar behavior for other things we have implemented with Phylanx as well. Another example, and that gets me back to the astrophysics application I mentioned in the very beginning, where we wrote an application using HPX, an astrophysics application that combines three different types of physics: hydro, gravity, and radiation transport. And these three models that are kind of combined in the same application and are being evaluated on a adaptive mesh refined, using an adaptive mesh refining methods, all have very different time scaling behavior. So combining these three models into one is normally a big challenge because it's very difficult to keep the system really busy running if you do that with conventional means. Just to demonstrate you the adaptive mesh refinement behavior of that application, no surprises there. This video just gives you an example that kind of depicts a couple of time steps of the evaluation. And you see very nicely how the different refinement regions, I hope you can see it over Zoom, how the different refinement regions are coarsening the further away you get from the system, and how the mesh is adapted where the actual physics happens in the center of those two suns. Some scaling results from that application. These results are collected on DAINT, PIT-STAINT, which is the largest computer in Europe. It's a GPU machine located at Lugano at the Swiss Supercomputing Center. This graph is a bit difficult to read, so let's focus on the blue lines only. What you see here is 4 strong scaling graphs for this application for 4 different problem sizes. Whenever the scaling of a problem was too small, we switched to a larger problem size and started to do a strong scaling study with a larger problem size. And this graph shows you the scaling behavior of the application from essentially 1 node to almost 5,500 nodes, and the speed up is quite significant. What we have seen that we get a weak scaling efficiency of about 80%, well, 78% from 1 node to 1,000 nodes, and a strong scaling efficiency in this example from 500 nodes to 2,000 nodes of about 68%. Thanks to the futurization techniques I explained before. So what did we get? I started off with this image, and if we look at the same application after some futurization, we see that the utilization of the cores has improved quite nicely. The utilization gaps between the core for the cores are gone because we are able much better to overlap all the ongoing parallel operations in the system. From the standpoint of the integration of different tools, what we would like to go for is to have a uniform API that allows us to handle all kind of parallelism in the system. And I think that the recent events in C++ and the standardization of C++ are very promising that they will deliver exactly that. I'm very eager to wait for the executor, the results of the executor standardization, which are expected to happen in 2023, because those executors will help us to get to exactly that goal. It's an underlying abstraction that will allow us to expose all the parallelism in the system, and I mean all of it, through a uniform API and integrate that well with asynchronous execution, as demonstrated in this talk. So the bottom line of my talk is, please futurize all the things that will help you definitely to speed up the execution of your codes. Thank you so much. So I'm more than happy to take questions and to try to answer those questions if you have any. Thank you.
Great. Thank you very much. Very interesting talk. I have many questions, but I don't know if I should go into my questions first or let the audience speak. I haven't seen a question in the Google Doc, but if someone wants to, well, let me ask a question. In the meanwhile, you can type something in either the Google Doc or the chat channel. A very simple clarification question. First, on your slide 23 and 24, where you had the 2 co-awaits, the second co-await for recursive call to the quicksort, can it be skipped? Can we not do that co-await and just pass the future down so that the recursive call waits for it?
Give me a second to get there.
Yep.
That one, yeah?
Yeah. Or if you go to the previous slide, it's the same. Yeah, right. That
one, right? You're asking whether this co-await can go away.
Yeah, that's correct.
Well, you can't, because when all gives you a future, and well, to explain what co-await actually does, that might be in order. Co-await takes a future and attaches the rest of the function as a continuation to that future. So it is a compiler-based transformation of your function where whatever comes after the co-await expression is attached as a continuation to the operation you're co-awaiting on. It's essentially a .then to the future that is returned from partition. The same is true for the future that is returned from when all. So in this case, it attaches an empty continuation because there isn't anything afterwards. And that's why you're asking, hey, do I need that? Well, you need it in order to compile things because while the function formally returns a future, the expression returned should be a non-future, which is kind of weird. But the function itself has to return something that is not a future. Do I have an example here? No, I don't.
But I think I understand.
Yeah, and as you see it in the end, right? There's no return statement in the end. So it essentially returns void, which is a non-future, but the compiler pretends that and wraps that into the future that is returned from the function. So it's more of a syntactic requirement that I have to co-wait for it because I can't return a future from the function. And the other thing is I have to co-wait for the recursive quicksort operations because when I go up, again, one level up, I have to be done with my recursion before returning. Otherwise, the node higher up will do nonsense because if the operation in the recursion is not done, you can't continue.
I see. This is maybe some kind of a lazy evaluation type thing that I was thinking about, that you can keep passing the future until you really, really need its value. And at that point, you block for it.
Well, the trick is that co-wait is not blocking. As I said, it attaches a continuation and returns immediately. And whenever that future becomes ready, that continuation is triggered later on. So it's really a lazy evaluation, as you say. It's essentially syntactic sugar for what I showed on the previous slide. So this is equivalent code, which is completely semantically equivalent to what the co-wait is doing. It's just simplifying the way we write that asynchronous code and significantly because nobody wants to deal with the .thens and all these continuations explicitly. And co-wait is doing that for us by applying compiler transformations to the function the co-wait is used in.
Okay. Benson, your question next. Would you want to ask? Otherwise, I'll read it.
Okay, I don't know if you can hear me.
Yes.
I guess I was asking, what's the likelihood of consensus on a distributed memory C++ model that is standardized? So you mentioned that there are a lot of different models that people have tried, but no agreement on maybe some minimal subset that could be standardized.
That's an excellent question. If you have ever attended a standardization meeting, you know that it's more political than anything else. And that's probably not specific to the C++ standardization process that is happening everywhere. So I have no idea what the likelihood of that is. It would require that somebody spearheads it and comes up with an idea. Because standardization is not sitting and discussing ideas. Standardization is assessing proposals. So if somebody has a proposal and proposes it to the committee starts discussing it. But without a proposal, nothing is being discussed. And I haven't seen a proposal for distributed memory, for a distributed memory model at this point. On the other end, and that's our experience with HPX, shows that you can get away with the C++ memory model as long as you have certain things in mind when writing your application. Namely, as long as everything is local, you're inside the rules of the C++ memory model. And once you get over the wire, all bets are off anyway, right? So the burden at this point is still on the programmer to make that happen.
So I have a question. It's going to be a little bit longish question, but I really want to know your thoughts on that. So first, let me preface with a couple of things. One is that in Cham++, we stayed with a very, very tame old C++. And part of the reason for that is because early on we had success with NAMD, which was being used on dozens of supercomputers and so on, and some of them would not upgrade their C++ compiler, so we couldn't just do it. So until just a couple years ago, we couldn't even go up to C++ 11.
Yeah.
But now we are unshackled. We feel a little bit freer than that. But leaving that aside, if I had full freedom too, there is a question that arises, and I think this question has to do with, I have seen over my 35 years a variety of C++ based attempts or other attempts at abstraction in parallel programming. And one tension there always is between simplicity and elementariness. I don't know how better to explain it. The best thing I can say is another anecdote, which hopefully some of you will find interesting. In 1985, when I was interviewing for a faculty position, I visited Indiana, where there's a Friedman and Weiss. Friedman was my host there of the Friedman-Weiss scheme and Lisp fame. So we were discussing various things, and he said something interesting. He said, I want to design a programming language for Einstein. If Einstein were to write a program, he should not be shackled by the programming language. His creativity should be matched by what the programming language provides. And the masses, well, that's not what I'm designing it for. So sometimes, now the tension here is that you get a complicated abstraction. Admittedly, some of the complexities in the implementation, you want to make things nicer for the programmer. But sometimes it's not nicer, it is briefer, right? Brief doesn't always mean easy to understand.
Yes.
How do you see that tension between brief and easy to understand abstractions?
That's a question we can talk about for hours, I guess. Well, it really depends on the target audience, right? If your target audience is C++ programmers, like plain HPX, then I think I tend to provide an API that is more explicit than easy to use or simple. As long as the API is consistent and composable, that would be most important for me, to have an API that is rooted on, for instance, on a C++ standard, right? So if somebody has done work in C++, it's not a big deal for them to start using HPX, for instance. So a very consistent, very concise, symmetric, uniform API. That's one of the reasons why we decided to use the HPX future as a central piece of synchronization everywhere. So whatever task you do, whatever operation you kick off, you always get an HPX future back, which you then can combine into these execution trees. If your target audience is more of a non-C++, non-HPC related programmer, like the domain scientists in machine learning, right? They know how to use Python and how to use NumPy, and that's it. Then we have to invest much more effort. And then you don't want to expose all that asynchrony directly to the user, because the user really thinks in terms of, hey, I have this array, I want to add those things done. And that's what we have tried to capture with that Phylanx project, where plain Python code is transformed into a synchronous execution without the user even knowing that it's asynchronously being executed. So hiding those complexities behind application-specific frameworks that expose the semantics the domain scientists understand. So it really depends on the target audience in the end and what you want to achieve. If I write a C++ program, I assume that somebody looking at it knows C++, and I don't care. And I'm not afraid to use more complex things. But if I'm writing a Python program, I'm trying to be Pythonic, right? I'm trying to provide APIs that the Python programmer can use.
I see.
Not sure if that answers your question.
No, yeah,
I wouldn't want to implement a programming language for Einstein. Definitely not.
I see. Okay. All right. Well, good. Any other questions?
Here's a question: how do HPX efforts relate to other standardization efforts like SYCL and DPC++?
Yeah.
Michael Wong, the vice president in CodePlay, he is responsible for SYCL. He is very active in the standardization committee. You might have heard of him. SYCL is definitely driving the standardization process based on the use cases SYCL provides. And in that regard, it's very similar to what we try to do with HPX. Those results and those experiences we have collected with HPX are used to drive the standardization or give feedback to existing standardization proposals, right? If somebody comes up and say, hey, I would like to do this, like reflection. Reflection has to be part of C++ standard. And the first thing I told them, hey, can you reflect on the captures of a lambda expression? And they said, no. I said, oh, but I need that in order to do proper serialization in C++. Otherwise, I am not able to send a lambda over the wire, which is one of the limitations today. We can't really do that if the lambda has captures. There's no way to stay in the language and still send a lambda over the wire and deserialize it on the other end. So all we can do, and please understand, LSU is only a small player in the standardization process, because the big guys like Google, Apple, Microsoft, and others, IBM, Intel, are much more politically powerful in the standardization than we can be. So all we can do is to provide feedback and say, that's nice, but that breaks this use case. Or that's nice if we added a particular feature to it. And that's what we're trying